This is the ChimeraX window, and we have some tabs at the top with different things we can use. There's a menu bar, and you can change the tabs here by clicking each tab. This is the home tab. We will use the command line a lot. So for example, we can open the map, open with the command open. The ID is 45793 from the EMDB, which is the database where pretty much all of the cryo-EM and cryo-ET maps and models are indexed. So if I run this command, it will open the map, and in the main graphics 3D window here, I can rotate it using the left mouse button, and I can control what the right mouse button does with this tab. So right now it's on translate, so I can translate, and you can also assign many other functions that we will be exploring. As a shortcut, you can also pan using shift left mouse button, and one useful thing for the right mouse, for example, is to change the center of rotation. So that's pivot. So if I select pivot, then I right click on a point, then the rotation is around that point. So this is very useful. And a shortcut for that is if I do option or alt and left click, and then it will center to that point, and then I rotate around that point as well. So that's also very useful. So when I open a map, the volume viewer dialog comes up. So these dialogs are independent. They can be moved around or also docked like this, and you can change the size. We will notice that it's using a step of 2 for efficiency, but to see the full detail, I will change it to 1. And this plot is basically a histogram of all the map values. So there's these are high map values on the right and low map values on the left, and I can change the contour level that is being used to display the map by dragging this bar. So if I drag it to the right, it's showing more dense regions, more regions with higher map values. This is an ISO contour, so that means that all the points along the surface are the same value, which is represented by this bar. So if I drag it to the left, you will notice with cryo-EM data, what tends to happen is all of the background noise starts to appear. So we focus most of the time on higher contour levels that is showing the actual atomic models. You'll notice the background is black here by default. For making images and visualizing, white is sometimes better. So you can change that by clicking on white there. And there's a nice rendering mode for surfaces, which is soft, and this shows it shows a bit of the darker regions are more inside, so you can see a little bit better the depth. Now let's open the model. So I will also use a command for this. It's I'm going to use open, and the ID is 9CPK, and atomic structures are stored in the PDB, so it's from PDB. So this model comes up, and you'll notice in the log here that if the log isn't displayed, you can go to Tools, General, Log, and then it will come up. And it will summarize what's in the structure. So there are chains, which are either proteins or RNA or DNA. These are chain-like molecules, and each chain has a different letter associated with it. So I can also click on A, for example, and then we'll select chain A or B or C, and so on. And then there's also some other small molecules, which are, for example, ADP and some ions. We will focus on the protein mostly. So I can hide the map by clicking this eye icon here, and now it's showing just the model. And here the default display is to use a sphere for each atom. We can change that under molecule display, and for example, I can make it stick instead, and now it's showing the bonds between each atom. Can do ball and stick. We'll keep it on stick for now. And another less cluttered way of visualizing a protein is to show a ribbon that goes through the backbone. So I can show the ribbon by clicking show on top of cartoons. And here I can hide the side chains. So now it's just showing the backbone as is a cartoon as a ribbon, and the alpha helices have these are a little bit wider, and beta sheets are also these wider segments. Now this structure is symmetric. It has 16 proteins, and the symmetry means that each protein looks is more or less the same. So we will focus on just one protein for simplicity. With the command line, we can also select each chain. We can enter cell, which is short for select, and then / and A, which refers to chain A, and we will see that it becomes selected. So we will focus on this chain, and we will delete everything else. So we can type delete and then chains B to P, and that leaves just chain A. We can turn the map back on and see where the protein is in the map, and we can visualize the map only around the protein by masking or zoning. So we will use the command vol, which is short for volume, zone, and now we enter the ID of the map, which is shown here. I should also open another dialog which is useful, which is the model panel, and the model panel shows all the maps and models are open. We have the map and the 9CPK model. So the ID of the map is 1, so I enter number 1, and I want to zone near the model 2, which is ID 2, and then I can enter a range, which is how far away from each atom it will keep. So we will, for these high resolution maps, a range of 2 angstroms is usually good. And I want to create a new map, so I type new true, and then also minimize the dimensions of the map, which helps to save memory. So min true. So this will generate a new map. You will see it appear in the models here, and we can see the map just around this one protein. I can change the color of the map by clicking this color patch either in the models or in the volume viewer, and then a color picker dialog will come up, so I can change this back to gray, and I can also make it transparent by changing the opacity. And you'll notice here this this rendering style, we can change to simple, and that tends to show these transparent surfaces a little bit more clearly. So we can also turn back on the atoms display, which will show the side chains along the backbone. And we can zoom in to see the side chains a little bit better, and we can see we can change the color to the default colors by doing actions color by element, and now it will draw nitrogen's blue, carbon's gray, oxygen's red. So this helps to see the different types of side chains. So if I zoom in here to some side chains, we can see that some side chains have density around them, and I can change the contour level with the bar, and you can see more density appear. So I'm showing slightly less dense contours here, so you can inspect side chains this way. At very high densities, less atoms are resolved, typically the backbone. So I can visualize the backbone a little better by turning off the ribbon. So I can say hide the ribbon, and you can see that the backbone has good contours around it, good density. So this is the backbone, and the side chains appear, some side chains appear at more lower contour levels, and some side chains might not be resolved. For example, some of the atoms in the side chains are not resolved, and this can be because either it's flexible, so it has its different position in each particle. Remember that this map comes from many thousands of particles averaged together, so if the side chain is different in each particle, the density around it will be blurry or average. Let's look at Q-scores, which helps us to identify which residues are resolved in different parts of the protein. So I run Q-scores from tools, more tools. By default it won't be installed, and then this will bring up the ChimeraX toolshed. And then here under model validation there's a Q-score plugin, so you click on it. For me it's installed, but if it's not installed you would click this button and then it would be installed into ChimeraX. Then it will appear under tools, validation, model map Q-score. So here's the model map Q-score dialog. Now when I have a lot of dialogues here, it can be useful to dock them together. So if you drag them on top of each other, they will become docked, and now I can change between them using these tabs. So now I have the Q-score dialog a little bit larger here. So I select the model first, which is number 2, and then there's only one chain right now, and then the map. Here I can select either one because this map includes everything. I will choose the full map for now, and then I type calculate, or I click calculate. So now the Q-scores are plotted on this plot, and we can see for each residue from 0 all the way to about 500 residues that are in this protein, a Q-score. Each point represents a residue, and I can click on this point and it will zoom into that residue. So right now it's showing the zone map, but what it's actually, it's also zoning automatically this full map. So here I clicked on a residue with high Q-score, so there's good density around it. In this map that is zoned, I can play with the contour level and then inspect each residue. And some residues might not be resolved, so as we talked before, so this is a long residue which is usually flexible. If I click on a point with a low score, these are residues that tend to be not resolved, like this one. So this one, the backbone is resolved, but as you go further away, the density becomes weak, and we consider these as partially resolved or less resolved. Now to go back to the full display, I will control click outside, and this deselects everything. And then if I go to show the ribbon, it will show, if nothing is selected, it basically applies to everything in the scene. So when I click show, it's applying this to everything in ChimeraX. And you'll notice it's a little bit foggy here because I was looking at a small part. So to reset the view, I can just type view, and then it will reset that so I can see the full protein. And to unzone the map, although this is the full map, if I did want to unzone it, I would type vol unzone and then the ID, so number 1, and this goes back to the full map. Let me go to back to this map for now, which is just the protein. And now that I calculated Q-scores, I can also visualize the Q-scores on the ribbon. So to do that, I have to recalculate them, but with this option checked, so assign atom attribute. And now I hit calculate again, and then it will assign the Q-score attribute to each residue. And then I can use a command to color code the ribbon. And this command is color by attribute, and the attribute name is Q-score. And here I can put range 0 to 1. Q-score is range typically from 0 to 1. But it's more useful to do something like 0.8 because that's the maximum Q-score here. So Q-scores vary by resolution. At this resolution that we have here, about 2.6, typically the maximum is around 0.8. And then I will enter average residue. So this average is the Q-scores in each residue over all the atoms in the residue. And then I want to generate a color key, so I say key true, palette, and then I want to change the palette so I know what I'm displaying. So I will go from red to a blue. I'm going to use a softer blue, so instead of blue is a little dark, so I'm going to actually put in the RGB values, 0.4, 0.4, 0.9, so this makes the blue a little bit softer. And this color key dialog will come up, and here's the color key, so it goes from 0 red to blue. And this is a good way to do a quick visual check. of what's resolved and what isn't in the protein. So you'll notice some parts here that are not resolved or noisy or red, and the parts that are resolved well are blue. It's also a good way to check for anything that is not fitted properly. So sometimes the model won't be fitted properly as it's being built or refined. So this helps me to find areas where I can improve the fit to map. To make the color key a little bit more like this, so here we can see that very low Q scores are yellow. So I can instead of going from red, I can go from yellow to red to the slight blue. So now the parts that are really noisy and not resolved are yellow. There's not too many, just a couple here. Okay, in the exercise that we will do for the class, we will export these Q scores to a file and then do some statistics on them. And to do this, I will use a script. And ChimeraX, I can open the general shell. And this is basically a Python shell where I can run scripts, and this will help me to export the Q scores. So I will enter, I will provide the scripts as a separate file, or it's in the assignment step-by-step guide. Basically, I just enter it here. You will notice that it's going to export them to this file. So here you can change this to a file on your computer. And to run the script, I just press enter at the end. And if I bring up my desktop, I will see this file appear here. And I can open this file, for example, using Microsoft Excel, or it can also be read in with a script and analyzed. So here I will have the first column is the residue type, so glutamate, asparagine, methionine, and so on. This is the res ID, so residues have increasing numbers along the chain, and then the Q score averaged over all the atoms in the residue. So I can do something like create a plot, as we saw, much like in the Q score dialog, and I can change the style of this plot in various ways. So, for example, I can change it to a marker instead of a line, instead of lines. So this is a simple plot that shows the Q score for each residue. And what we'd like you to do for the exercise is to look at some statistics for residues, for different residue types. So for example, in Excel, I can sort these by the residue name. So now I have all of the residues sorted by name. And I can average, for example, all of the Q scores for the alanine. So I can do something like equal average, and then select the Q scores for all the alanines. And I can also calculate a standard deviation of the same, and I can do the same for the arginines. Average overall the arginine Q scores, and then also calculate the standard deviation. And I can create a new table with these values. So my first one is alanine, and the average Q score is 0.663. Standard deviation is 0.07 about. And for arginine, 0.621, 0.113. And then I can create a plot for these. In this case, I can use a bar plot, and then here I can control the range, so I can go back to something a bit lower. So they're pretty similar. but there might be different variations for different types. And here I can set the labels to be the names. And I can also add error bars to signify the standard deviation. And this is under chart design, add chart element, error bars. Now this is just some standard deviation that I can then select these values that are calculated. So here by default is just set to 1, but I can choose custom, specify value. So the positive is this one, and then the negative will also be the same. And this way I can visualize the standard deviation or the variation in Q-scores and hence resolvability for different residue types. So we would like to do this for all of the different types. There's only about 20. Can be done like this more manually or scripting perhaps with Python. And then we would like you to look at why they might have different averages and different variations in resolvability based on chemical properties. So if you can look up what different residue types are and what their properties are. For example, they might be more solvated, or they might be so they might be closer to solvent, or they might be more buried generally. And what are the variations in resolvability for these different types?